Right. So I didn't post anything yesterday because I was not feeling good. Even right now, I'm not feeling that good, but at least now I can do this, I guess. Okay, let's start. So first question. First is a what the vertical limbs of a U-shaped tube are filled with liquid of density rho up to height h on each side. The horizontal portion of U-tube having length what 2h contains a liquid of density 2 rho. Okay, so it's a U-tube uh, filled with liquid of density up to height h. Okay, density rho up to height h. The horizontal portion of the U-tube. What horizontal portion? What do you mean by that? Having length 2h contains a liquid of density. Okay, I think I know what they're talking about. So it's not exactly a U-tube. It's more like this. Okay, so this is h and this is h, and this is like rho, and this is 2 rho, and this complete thing is what? Uh, 2h. Okay. The U-tube is moved I thought it. Okay, it's moved horizontal with acceleration g upon 2 parallel to the horizontal arm. The difference in the heights in the liquid in the two vertical limbs at a steady state will be. Right, so let's just say that difference is x. So this is now x lower and this is x upper. And I assume it's like immiscible or something. These liquids are immiscible. I don't know. Anyway, so it's like, yeah, this is x over here and this is actually x over here. So this is filled with 2 rho. This is filled with rho, right? Here's the pressure. The pressure is just P naught, right? And it's what? So it's acceleration g upon 2 in some direction. Just say so it's g upon 2. This parallel to horizontal arm, of course. So g upon 2 pseudo force. Okay, pseudo acceleration this direction, right? So you come down, your pressure increases. Here's just P naught. Now it's gonna be what? So rho g. Then you got h minus x. Okay, that's your increasing pressure. Then over here, what happens is, so yeah, your pressure once again just increases. First you have rho. So you just have rho x and then g upon 2, I guess, yeah. Then you got 2 rho. So 2 rho, it's 2h minus x, right? So just 2h minus x times g upon 2. And then you go up. It's just so, there must be some better way than doing this, right? Some way that you can just, figure out what this is supposed to be. Okay, maybe there isn't. Whatever, just do it. So it goes up, right? So like decrease, and then it just what is this thing? Just 2 rho. What's this length? Just x. What's the height? Oh, that was the height. Okay, and then your what's the upward acceleration? That's going to be just 1g, right? Yes, like g upon 2. That's it. Okay, just go up now. So this is okay. This is the same stuff as h. This was 2 rho, right? This little block, and now this complete thing is just h, right? Yeah, I did everything correctly. Yes, it seems so. Now just that. So it's decrease and rho h minus x times g. That's equal to 0. All right. So what does that mean? Rho cancels. So g also cancels. This is h minus x plus x upon 2 plus, so you got 2 times all of this, which is 4h upon 2, which has to be, that 2 actually cancels with this thing. So it's just 2h minus x, then minus 2x, then minus h plus x is equal to 0, right? So this just becomes 2h. Okay, 2h, then minus x minus x minus, which is minus 4x plus x, which is minus 3x. So minus 3x plus x upon 2 equal to 0, which means that 4h minus 6x, that's plus, right? And this is all negative. Okay, okay, that cancels, and then it just negative 3x. Yes, that has to be, it's just plus x, that's 5. That's equal to 0, which means that x is equal to 4h upon 5, which is not here, of course, because now is that not here? I messed up somewhere. That has minus x, of course. This is going in that direction. There is a pseudo force. Sure, it has to be increased. Uh, is that 2h minus? Okay, that happens. And then what about this guy? So g upon 2 and it's just x in that direction. Should have worked out. Should have worked out. Why is this not working out? 2 rho in there. This is 2h minus x. Yes, this distance is in fact just 2h minus x. G upon 2 and then got. So that's increase and now it's decreasing. So yeah, I mean that has to be thing. Sure. It's decreasing by that. It's just minus 2 rho and must be some other way. I think. What's going on? It's just minus 2 rho times x times g. Okay, yeah, that is the thing. And then it's also is the oh, it's not h minus x. It should just be h. It should not be h minus x. Okay, then this is right. Okay, that's what went wrong. Okay, okay, okay. So then you don't have this over here, which means it's just minus 4x over there actually. So this will be minus 8x plus x is minus 7. So yeah, 4 upon 7. So C is the answer. Next question. First C. Second. This is so clunky. Second is a bucket contains water filled up to a height of 15 centimeters. The bucket is tied to a rope which is passed over a frictionless light pulley, and the other end of the rope is tied to a weight of mass which is half of that of the bucket plus water. Okay, bucket contains water filled up to height something. So height is 0.15 meters. The bucket is tied to a rope which is passed over a frictionless. So this is the bucket. It's tied to a rope which is passed over a frictionless light pulley on the other end of the rope. Okay. Okay, another end of the rope is other end of the rope is tied to a weight of mass which is half of that of the bucket plus water system. So this is okay, okay, understand. So this is a well, we don't know what the mass is though. Just say this thing is m, this will be 2m, right? Okay, the water pressure above the atmospheric pressure at the bottom is right. Just figure out the acceleration. Cool. So how do you get that? Oof. This is yeah, okay. This guy's energy or something. Oh, we don't need to do that actually. Just do it. Well, it's just a single string system. So you can of course do that, but whatever. It's gonna be what 3m upon 2 times v squared, right? So d by dt of this thing that's equal to or just plus d by dt of the h thing. Okay, you know the thing, right? So just d by dt, right? Okay, what's that going to be actually? So that will just be mg, and then yeah, well, that x stuff that will just be negative. Oh, actually, this is going to go down. So actually, ngv, this has velocity, of course, and then just have so minus 2 mgv equal to 0. Sorry. So 3 mv acceleration is equal to mgv, which means that acceleration is just g upon 3. So this has g upon 3 acceleration. So well, okay, it's going down, right? So this is going to be up. Okay. And what's this guy's height? It's just this. It's just the atmospheric pressure. So at the bottom, it's just atmospheric pressure minus rho gh. So rho g times, yeah, okay. And instead of g, you should actually have, wait, there's that pseudo force. Moreover, there's also the normal gravitation that you have. So it's g upon 3 downwards. No, 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 no. Pseudo force is zero acceleration is just g upon 3 upwards. So combine just 2g upon 3 downwards. Okay, so just this, and then you got 2g upon 3, and yeah. So what do you want? The water pressure above atmosphere pressure at the bottom is just this thing, of course. So it's water, right? Oh, that's also in centimeter. You know what? Just use centimeters. So one gram per centimeter cube. 2/3. You want G, which is just 10 meter. Okay, whatever. First of all, just H, right, which is 15 centimeters, and that terms of G, which is just 10 meter per second square. This is one answer. Why does it feel like I'm really slow right now? Okay, it's just 10. So what is this thing? 100 upon cent. Okay, 100 and got gram per centimeter square times meter per second or whatever. So 100 times 10 power negative 2 upon 10 power negative 4 in SI units. So that will just be what? 10 power 4, right? That's the, oh yeah, that's actually in SI units. So 10 kilopascals, right? Wait, what? 5 kilopascals, 1 4. How does that happen? Something went wrong. That was 10. For sure, that was also 10, so just 100. And then this is, could either be 1 or that. Well, something doesn't look correct. Oh, okay, a gram is not this thing, it's 10.83, sorry. Okay, so it's 1,000, right? Which is 1 kilopascal. So B is the answer. Next question. Let's go to third. Really slow right now. A cone of radius r and height h is hanging inside a liquid of density rho by the means of a string as shown in the figure. The force due to the liquid acting on the slant surface of the cone is. This is a cone. On what? The slant surface of the cone. The force due to the liquid. And it's just hanging like that, right? Oh yeah, just the. Oh shit, the pressure varies, right? Should raise with height. Oh. Uh. Okay, and what is this? Like, this cone is hollow or what? Does it even matter? And just hanging inside, right? There is this tension and whatnot, but okay. You just want to force it to liquid. Oh, so we don't care about the tension at all. Actually, you know what? Yeah, just do the integration and get the thing done. So you got some pressure over there, and wait, okay, that's atmospheric pressure, and then you have this thing. Wait, why is there no P naught involved in there? There should be P naught involved, right? Or not? Something doesn't feel correct about this. No, there must be P naught involved because it starts off at the pressure P naught, right? So it must be there. Force due to that. So do we like have to think about this thing as well or what? Oh god, it's not making sense. This is not making sense. Maybe what if they gave us a thickness? That would have made sense, right? But now you can't do it because radius r, height h, Islam. So I think what we should be doing is like just figure out the actual force on this thing, right? And how you figure that out? Of course, the volume immerse times. Yeah, okay, that was the thing. I don't like that. The problem is, what's the atmospheric pressure? We don't know that, right? Yeah, we don't know the atmospheric pressure, but there should be some kind of atmospheric pressure. That's not involved in there. How does that even make sense? Okay, so what is the total buoyant force on this thing? We just the density of this thing as okay, rho g times volume. So rho of the liquid, right? If rho g times the volume of this thing is what? It's 1/3 pi r square h. So yeah, and that's not here, of course, because they write really bad questions. It's supposed to be having a p naught factor inside, but hey, okay, just assume p naught equal to 0. Maybe that's what it is. That's what they're trying to do. Whatever. In that case, yeah, just figure out that other factor. So just integration of. So you got rho g h. The h increases. The h is the depth from that, right? And you want okay, what is the xy area of this strip, right? So this is our dh. This thing is our r, right? What's the xy area? It will just be 2 pi r, and then dr. Well, dr is what? We can figure that out, right? Okay, you know what? Yeah, this is it. This is the area. So this times 2 pi r dr, and this is going from r equal to. Okay, we just have to write h in terms of r. So you can do that like this: h upon capital R times h. Oh, that times what am I writing? Times small r, right? Okay. This is the thing, and it's going from r equal to 0 to capital R whole. So rho g, okay, that is comes down. So this term 2 pi rho g h upon r integration of what? R power 2 dr is r cube upon 3, just capital R cube upon 3, right? Just be this thing squared. So yeah, 2 pi rho g. Okay, there's 2/3 involved in there, so it will be d. Although that's definitely incorrect because you should also have atmospheric pressure involved in this, but whatever. D is the answer. Next question. Fourth. Fourth is the area of cross section of the wider tube shown in the figure is 800 centimeters square. If a mass of 12 kg is placed on the frictionless piston, the difference in heights h in the level of water the two tubes is. What? Okay, the area of cross section of the wider tube is 800 centimeters. So area is what? I hate when they put it like this. 10 pound 82. Okay. If the if a mass of 12 kg, so m equal to 12, is placed on a massless piston, the difference in height h in the level of, oh come on, seriously. So what do you want is mg upon a, that's the increase in pressure, right? So just p naught plus that pressure. So yeah, this is equal to what? This is equal to rho gh. That's it. So just means what do you want, by the way? You just want h, right? H is just what, mg upon rho g, which is m upon rho times a, which is 12 upon, actually one row is 10 power negative 3 upon, well, 10 power negative 6, which should just be 10 power 3. So 10 power 3, that's our row of water. This is water, right? I believe this is water. Yeah. What else could it be? So just water, right? Okay. I mean, it of course depends on what this thing is, because how else are you going to do it? It's kind of a weird thing. Maybe there's some other way. The work done stuff, right? Yeah, that would be a way to be thinking of. Okay, I don't like that because of, okay, so it goes down by something and that goes up. So we don't know what the cross section of this is, right? Yeah, so there's no way we can do that. So you have to use the density of water, otherwise nothing, yeah, that you can do. So this is the density of water times, what was the factor A? Area is just this thing, 8 times 10 power negative 2. Between it's just 12 upon 8 times of 10 power 1, just like 12 upon 18. So 3 upon 20, right? And this is in meters, I think, so it's 15 centimeters, which is C. Next question, fifth. Fifth is a fluid container is containing a liquid of density. What is this? Rho. Okay, fine. A fluid container containing of containing density rho is accelerating upward with the what? With acceleration a along inclined what? Inclination alpha. Okay, fine. Then the angle of inclination. Come on. What is this? Why are you writing rho everywhere? The inclination of the free surface is. So okay, this should be theta. This should be theta, I think. Right. So you want to figure out what theta is, right? Okay. There's mg cosine theta in that direction, whatnot. Fine. So what do you have? This is inclination theta of this thing. Cool. In this guy's reference frame, you just have acceleration like this, and you also have like g cosine theta. And so the thing is, like, this should be completely normal to this guy, right? Yeah, in that case, it would not go down. And then you also have this, oh, it should be g sine theta that direction. So there's g sine theta acceleration. And then this is g cosine theta in this direction, right? And this is completely normal to this vector, right? So this vector, yeah, which means it's making what angle with the x-axis? I mean, this vector was angle theta is, yeah, so just 90 minus theta, right? Yeah. So g cosine theta upon this thing is just tan of this guy. So what does that mean? Cot theta. Yeah, okay, that just means tan theta is equal to reciprocal stuff. So tan theta is equal to a plus g sine theta upon g cosine theta, just like, oh, we really have to do this thing. Okay, so that's it. B is the thing. Oh, why am I using theta everywhere? It should be alpha, whatever. So B is the answer. Next question. Sixth. Sixth is figure shows a three-armed tube in which a liquid is filled up to levels of height L. Okay, this is a okay fine. It's now rotated with an angular velocity, angular frequency about an axis passing through the arm B. Okay, the angular frequency at which the level of liquid in arm B becomes zero is. So this just goes down and then okay fine. So by symmetry, well, this is like L, right? So it's gonna go up by L upon 2 and L upon 2. So this, yes. Yeah. So when does that happen, right? Okay, no big deal. Uh-oh, because it's gonna be omega square R. Okay, and these three arms are open to atmosphere, I think, right? Okay. So what's the integration through this thing? So just integration of, it's supposed to be rho gh, but then now just the g varies, right? It's just rho times dh, and then instead of g just have omega square r. Because yeah, as the thing, then it's of dr. That must be the thing, right? Yes. Just do the whole thing, right? The differentials work out, and then it's just the thing. So yeah, that's the change in pressure as you go from here to here. Like the pressure is gonna decrease, isn't that right? Okay, so it should be going from here to here, whatever. And it's like indication from r equal to 0 to L. So it's just rho omega square, and you got r squared upon 2, so L squared upon 2. So that thing is equal to, and now it's up. Um, yeah, right. So just like how much is this up? Same cross section as of these three cubes, which means it should be L upon 2. So that's equal to rho g times 3L upon 2. Cool. What does that mean? Just like omega squared L is equal to 3g. Well, that 2 stays because, right, this cancels. It just 3g, that rho cancels. Yes, that's the thing. So what does that mean? L is equal to, wait, what do you want to figure out, by the way? Oh, you want to figure out omega. So omega just square root of 3g upon L, which is C. Next question. Seventh. Seventh is an open cubical tank was initially fully filled with water. When the tank was accelerated on a horizontal plane along one of its sides, was found that one-third of the volume of water spilled out. Fully filled, okay, fine. The acceleration was, so one-third of the volume filled, sorry, spilled out, right? Ah, right, so this is the new free surface that you have, and so this volume that is not here now, that's just one-third of the volume. So it's a cubical tank, right? Let's just say this thing is one. Okay, let's use L because right, and let's say this thing is X. So what do you know? This volume must be one-third. So like half X times L. All right, that's this area. It's just equal to one-third of L squared, which means X is just equal to two-third L. Okay, so this would be two-third of L. So just draw a better diagram. Whatever. That's just too much. So two-third L. Okay, this spells out, right? So yeah, I'm just say this angle is theta. Then you know that tan theta will be what? So tan theta is two-thirds. Tan theta is two-third. But then as you saw in the last case, right? Wait, first of all, how is the gravity thing acting? So it was of course accelerating in this direction, right? So pseudo acceleration for this guy in that direction. So that's in this direction, and there's gravity. So just say this is A, this is G, right? And yeah, this is the surface that we are having. This angle is theta. This angle will just be 90 minus theta. Just pull it over here, and that just means, yeah, right. So tan of 90 minus theta is equal to G upon A, or tan theta equal to A upon G. Looks cool. Sure, it looks cool. So just A upon G is equal to this thing. So G, A equal to two-third of G, which is B. Next question. Next, eighth. Eighth is some liquid is filled in a cylindrical vessel of radius r. Let F1 be the force applied by the liquid on the bottom of the cylinder. Now the same liquid is poured into a vessel of uniform square cross section of radius of side r. Okay. So was it in a cylindrical vessel, and now it's poured into a vessel of uniform square cross section, okay, of side r. So volume remains constant, right? Let F2 be the force applied by the liquid on the bottom of the vessel. Then once again you have to take atmospheric pressure into account. You won't. God. You should have at least said excess force applied or something like that, right? This makes no sense. You're assuming P not equal to 0. That's wrong, but whatever. So in this case, what's the height of this thing? Some liquid, right? So cylindrical vessel R or whatever, right? Let's just say it has some height h. So pi r squared h, that's the volume, that's equal to. So now what height will you have? So it's r squared times h dash, which means h dash is just equal to pi times h. So what do you want? You want the force, right, which is proportional to h. So, right, f dash or f2 is equal to pi times f1. So, yeah, f1 equal to f2 upon pi. That makes sense. So, B is the answer. Next question. Ninth is a liquid of mass 1 kg is filled in a tank as shown in the figure. The force exerted by the flask on the liquid is how much? So by the flask on the liquid, and of course just equal to the weight. What else would be the thing? So like the complete flask, right? Not just a part of it. So yeah, it's exactly equal to 10 newtons. So yes, there we go. Next question. Wait, the atmospheric pressure. Okay, the atmospheric pressure is also there because oh, okay, neglect. Okay, you should have told me. Yeah, then it's just 10 meters. Seriously though, you can't you just can you really just neglect the atmospheric pressure because in most scenarios you will have to take that into account, right? So whatever. Next question. A YouTube having horizontal arm of length 20 centimeter has uniform cross section area A equal to 1 centimeter square filled with water of volume 60 cubic centimeters. So start with the volume. 6 times 10 power, what is this thing? 10 power what? Wait, what? Okay, let's not hurry right now. We'll figure out the formula. So they gave us the volume, a tube of, okay, fine. Filled with water, first of all. Fine, because of volume. Okay. What volume of liquid of density something else, okay, should be poured from one side into the U tubes. Okay, U tubes so that no water is left in the horizontal arm of the tube. So horizontal arm is given. I don't get how do you call that a YouTube? It's more like I don't know. Okay, it is a YouTube, but not the way I thought it would be. So what you're saying is, so initially it contained what? It contained water of volume 60 cc. Okay. So now, right, when you put this fluid, you just have this thing. You just have this 60 cc volume like here, and assume it's immiscible liquid. Then so you have to fill it with that liquid. So that no water is left in the horizontal arm, right? So it's this thing. Cool. Maybe it's like this. I don't know. Right. So what is this volume going to be? Okay. Well, there's no horizontal acceleration, so there's no pressure difference along this thing. So just what is this height going to be? If this is h, then this will be h upon 4 because it's 4 times as dense. So yeah, just h upon 4, huh? Okay, and what about the cross section or what? Okay, so the whole YouTube has same cross section 1 centimeter square, huh? Okay, so it's just 60 cc. This volume will be just 1/4 of that, so it doesn't matter. Yeah, uh, sure, that has to be the thing. So just 1/4 of that, which is 15. So it's just 15 centimeter cube over here. And what about this thing? So you also have that volume. So just 20 centimeter times this thing is just 20 centimeter cube. So this plus that is 35 cc. Next question. So it's T, 10th is T. 11th. Am I going slow or something? Maybe I am. The pressure at the bottom of tank of water is 3 p where p is atmospheric pressure. If the water is drawn out till the level of water is lowered by 1/5. What? Oh, okay. The pressure at the bottom of tank will now be. Wait, what? Okay, till the water, the level of water is lowered by 1/5. Oh, so the 2p pressure is because of the water. Now you just have 2p upon 5, right? Because, yeah, it's 2p upon 5 extra, so it's p plus 2p upon 5, right? Which is just 7 upon. Wait, that's right, right? Level of water is lowered by 1. Oh, okay, it's just 4/5 of that. Okay, fine. So it's 4/5 of 2, which is 8/5. So 8 upon 5p and then plus p once again. So just 13.5, which should be b. Next question. 12th. An open-ended U-tube of uniform cross-section area contains water, standing initially 20 centimeters from the bottom in each arm. and an immiscible liquid of something they add to one arm until a layer 5 centimeter high forms as shown in the figure. What? Okay. What is the ratio of H2 upon H1 of the height? Okay, fine. So this is H2, this is H1, huh? Right. The ratio of these two. Standing initially at 20 centimeters from the bottom in each arm, right? So, okay, awesome. You want the ratio of these two. Oof, I don't like this particularly. So this is H2, this little thing, this is just whatever initial height you had. So, okay, that was 20 centimeters from each. So just say 2 capital H. Then just have this thing, so it's H1 here for water, and this thing is 2 capital H minus H. And then you have this water, this other liquid which is of, I don't know, some other density, and this is the remaining height. So just H1 minus 2 capital H plus H, right? Okay. So then just cut off these things. So difference of that from there. Oh, it should be H1 actually. So okay, that actually works out somehow. Isn't that weird? Okay, and this should be H1, and now this thing will be what? Just put, instead of H, just put H1. Oh, it should be H. Shit. It should be H2 over there. Okay, okay, just draw it correctly this time. So the lower on the left arm, you just have this thing. You just have 2 capital H minus H2, and then this is H1 minus 2 capital H plus H2, and then over here. So in this arm, like this is the thing. My head is hurting now. Right, so this just cut it like that. So it's just this completely minus that, which is H2 minus this thing, right? Yeah, which is going to be just 2H2 minus 2 capital H, right? Okay, so what do you have? What about the densities though? So it's 4 gram per centimeter cube, which is 4 times of the water density, right? Okay, so that just means this thing is 1/4 of that. Just okay. So 4H1 minus 8 capital H plus. Okay, just usually do the 2 cancellation and things simultaneously. Just 2H1 minus 4H plus 2H2. I hope this is correct. And it's equal to what? Uh, H2 minus H. So 2H1 is equal to 3 capital H minus H2. Right. This is the ratio. Okay, this is the thing. And what else was the thing? Oh yeah, wait. How much was added? Sorry. It's H1 and this is H2, right? Sure. Anything else you know about this though? You want to, okay, that's just one equation, you need another equation. So this is, it's not helping much. Okay. Some other thing that you can do. So, right, and that's just that. Okay, you know that much. Oh, okay. Also, this is equal to 5. That's important. So just H1 minus 2 capital H plus small h. 2. That's equal to 5, right? Yeah. Yeah. Right. 5 centimeters. Let's say it's X or something. Okay, just we are not solving it properly. We'll just do the thing. So yeah, just figure out what these should be. So our equations have 2H1 plus H2 is equal to 3 capital H. Initially it was how much of water? So 20 centimeter each, right? So just figure out 60, and this will be what? H1 plus H2 is equal to 2 capital H plus 5, right? So it will just be, am I doing everything correctly or not? I think I am. So just 2 capital H would be 40, and then 40 is 45, right? What does that mean? H1 is equal to 15 and H2 is equal to 30. Hopefully that's right. So this is 15, that just means like this is 10, and that's what that is 30, right? So 20, and this is 5. Yeah, that works out. So what's the ratio? H upon H, which is 2. Next question. So 12th, it's 2. 13th. 13 is a heavy hollow cone of radius r and height h is placed on a horizontal table surface with its flat base on the table. Cone on table, the whole volume inside cone is filled with water of density rho. Okay, the circular rim of the cone's base has a watertight seal with the table's surface, and the top apex of the cone has a small hole. So like this. Okay. Neglect atmospheric pressure. Find the total upward force exerted by water on the cone. Okay. The cone has this also has a small hole on top, right? The top apex. Yeah, it's like this. Okay, whatever. So that's what is. Yeah. So what that means is it's actually like this. So this is a atmospheric pressure, which is now 0 in this case. So it just goes down like that. Hey, isn't that the same as what we saw the last time? Yeah. So just want the upward force exerted by water on the cone. Right. It's just, yeah, I mean, just use that formula that we got the last time. Okay, no. Don't do it. Just do it properly. We'll derive it from scratch. It's just integration of what, so just remember what it was, 2 pi r dr, the horizontal area. Yeah. And then times of, what's the thing, the pressure of this rho gh. So rho g small h is like capital H upon capital R times R. This was just 2 pi rho g capital H upon capital R. That cancels. It's just yeah, integration of R squared dr. So just from 0 to what? 0 to this. Okay. What was the thing once again? Where did I go? Oh, right. So radius R, height h, cool. So 0 to capital R, right? Which is what? Just argue upon C and M, which is 2/3 pi rho g h r squared. That's the force, upward force, of course. Right. So yeah, this looks good. So A is the answer. Next question. 14th. 14th is two cubes of size 1 meter sides, one of relative density 0.6 and another of relative density 1.15. Okay, are taken by weightless wire and placed in a large tank of water. Under equilibrium, the lighter cube will project above the water surface at a height of what? Oh, okay. Project above the water surface under equilibrium. Okay, fine. So, yeah, one of them is light. Relative density with respect to water, of course, right? Okay, so just 0.6 for one guy, and this is 1.15. So it's this thing, like this, right? Yeah. So what are they saying? They are saying uh, the lighter cube will project above the water surface to a height of, and the cubes have size 1 meter, right? Okay, that's a side length, right? What was I going to do? Yeah, what was I going to do? Okay, what about this? Right, so let's just say this is x, then this will be 1 minus x, because it's just 1 meter, right? And then the whole volume that you have over there. Okay, do we need to do that? Maybe not. Maybe we do. I have no idea. Anyway, just 1 minus x times, well, the basically is just 1, so just that. And then you got this is also just 1, so this plus 1, which is like 2 minus x. So 2 minus x is the volume inverse. Well, that times the density of water in SI units times g, that's the buoyant force. That's just equal to the total weight of this thing, which is how much? So say rho 1 plus rho 2, because yeah, that was of g. So then this goes in the denominator, just rho w, and then just relative densities. This means 2 minus x is equal to 0.6 plus 1.15, which is 1.75. So x will just be 0.25, right? So meters, right, which is now 25 centimeters. So just please the answer. Next question, 15. 15 is a cubical piece of wood, has dimensions A, B, C, its relative density is D, is floating in a large body of water such that the side A is vertical. It is pushed along a bit. Sorry, it's pushed down a bit. Okay, the time period of SHM executed by it will be, okay, whatever. So the force on this or whatever, yeah, just say it's extra depth is just X and something, right? Uh, yes, like that amount of volume is what we have. So just two. Sorry, what am I doing? What am I doing? Okay, rho G. Rho is the density of the. Okay, so relative density is D, right? So rho of the solid. Oh God, sorry. What am I doing? What's the volume immersed? Just X. Let's just say the volume immersed is X. So X times of area. So just B times C. That's the volume. Okay, that times the density of water, that is of G. That's the retarding force. And upon the mass. So mass will just be ABC. What am I doing? Well, yeah, that is the thing, right? Okay, so just ABC density of the solid density. This cancels. So what do you get? Just get like X upon A and then relative density. So that's the acceleration. Yeah, or negative of that. And A is okay. I should just say W or something for acceleration. So yeah, the thing is just negative 1 upon square root of A times of D. That is our omega, or angular frequency. So you want time period, which is going to be 2 pi upon omega, just 2 pi square. Oh, which is not negative, sorry. This is negative, or they just, yeah, okay. So 2 pi square root of A times of E, which is what? Oh, okay, they didn't give us the thing. And G is involved in there somehow. Wait. Oh, we just want the mass, not the weight. Oh, yeah, that's why the G is involved. So just this. So it should actually have this thing. So just this and upon square root of G. So 2 pi square root of AD upon G, which is D, I think. Next question. So the reason why I didn't post anything yesterday was because I was not feeling good and basically just having headaches. And even now I'm having a headache or something. Okay, next question. A dumbbell is placed in water of density rho. It is observed that by attaching a mass m to the rod, the dumbbell floats with the rod horizontal on the surface of water. Okay, and each spear exactly half submerged as shown in the figure. Spears are half submerged. What do you mean by that? Okay, whatever. Fine. I get it. So the volume of mass m is negligible. Wait, what? A mass m to the rod. Wait. Oh, the volume is negligible, not the mass. Sorry. The value of the length L is. This thing is L, and the total length is what? Huh? What's the total? What's the total length though? Okay. So at least half submerged is shown in the figure. How am I supposed to figure it out if I don't know the length? I need to know the length of this complete rod. Oh, okay, that's D. You should have told me. Fine. Then it's doable. Okay. So yeah, just let's do the thing about this guy or something. So yeah, mg times d, that's the torque over there, and then there's this upward force, right? Okay, just have equal to, oh, it's not d, it's L, sorry. So mgl, that is equal to uh this is like capital Mg downwards, and what else do you have? And it's v upon 2. Oh, you don't have density of water involved, huh? Right, look at that. So then how do I do this thing? Since there's no density involved and that is the same force over there. Oh, I know a way to do this. So we don't know the buoyant force. Cool. That doesn't matter because the buoyant force is the same for both of these guys, right? Just take the point midway. Yeah, that makes sense. Let's just say this is our x coordinates, then our midway point just be d upon 2. So according to d upon 2, what is the torque? So just have, well, that buoyant force doesn't produce a torque because, right, cancels, right? So it's just, this is downward. This thing is also downward. Cool. So just mg times d upon 2 plus small mg times L minus d upon 2, right? Yeah, that's equal to, so this term would always just 2 capital Mg times, what's this thing? Okay, just d upon 2, of course. So just d upon 2. What does that mean? This means capital M times d plus small m times, oh, it's 2, right? So it's just small m times 2L minus d is equal to uh, 2 capital M times, no, well, just d, right? Yeah. And what do you want? We want L, of course. So yeah, this means 2 small m L is equal to d times of, well, okay, that cancels, just 1 capital M. It's just 1 capital M, and then you have 1 small m, right? Yeah, yeah, that makes sense. Just L is equal to what? Capital M plus small m upon 2 small m times d. So that's the answer. So it's just oh, it's d upon. Okay, you can also do that. So it's d upon 2. Wait, what are they doing? V and then what is this thing? V, what? What? What's rho? Oh, you are using density. Okay, sorry. This is a different thing in that case. That was very unexpected. Okay, some other way, right? Yeah, but this is also correct, and that is also correct, right? Okay, they are not using D, well, they are using actually. So, capital M plus small m upon small m, you need to do that. I hate this. What other equation can you use? You can also use the translational equation, and starting to not like it, you know. Okay, so you want everything using. Oh, you don't want small m. Okay, that's the thing. You don't want small m. You should have told me. So if you don't want small m, just take this point for our torque equations. Then yeah, what you will have is, so the buoyant force will be how much? It's just volume times density of water times g, right? Yeah, okay. Oh, so it's actually half of that. So over here, what forces do we have? We just have mg times, God. So just m downward, okay, minus v upon 2 rho upward times, well, you got g, but that doesn't matter actually. Times this thing, just d minus l, that's equal to 2m minus v upon 2 rho times that's what, l, yeah, just not feeling good. Okay, let's do it. So that goes with this, just 2m minus v rho times d is equal to L times, of course, so just 4m minus v rho and plus, so 2m minus v rho, right? That's our equation. So now what do you get? Just get L is equal to 2m minus v rho upon, well, that 2 comes out, right? So it will just be what? 3m minus v rho, and then you got d upon 2. Okay, so that's the thing. 2m minus v rho, or you can also write like this thing, v rho minus 2m. So 0 minus 2 upon 0 minus 3m, which is B. Next question. 17th. 17th is two bodies having volumes V and 2V are suspended from the two arms of a common balance, and they are found to balance each other. Okay, so if the larger body is immersed in oil, density D1, and the smaller body is immersed in unknown liquid, and the balance remains in equilibrium. Okay, huh, that's very weird. The density of the unknown liquid is given by. I mean, that force must be the same thing as that force, right? That's all that matters. The body, so if a larger body is immersed in oil, the other body is immersed in kind of other. Okay, so the largest body is of course 2v1, right? Yeah, just so 2v upon 2 times the density, so this t1, that has to be equal to v upon 2 times. So when they say it's immersed, what exactly is happening though? Yeah, like what is exactly happening? So it still is the same thing. Gravity is buoyant forces. The buoyant forces must be equal, right? Because how else will that actually happen? Yeah, well, sure, the buoyant forces are equal, but how much of the volume is actually immersed? Wait, when it says it's immersed, it's like fully immersed, I think. Right. Yeah, just assume the weight is actually very big and then we can immerse it completely. So what that means is, oh yeah, just no need for this upon 2 is just 2v times d1 is equal to v times of d2. So just, 2 times of this thing, just 1.8, which is b. Next question, 18th. 18th is a container of large surface areas filled with liquid of density rho. A cubical block of side edge A and mass m is floating in it with 4/5 its volume submerged. What? Container of large surface areas filled with what? A liquid of density rho. A cubical block of side edge A and mass m is floating in it with 4/5 of its volume submerged. Okay, if a coin of mass m is placed gently on top of the surface, why did they actually tell us about, okay, large surface area filled with density, whatever, with 4/5 of its volume submerged. If the coin of mass m is placed gently on top surface of the block, sorry, top surface of the block is just submerged. Oh, okay. Wait, what? It is just submerged. Grammar. M is. So right now M is floating in it with 4/5 of its volume submerged. So the 1/5 volume is upward. Okay, fine. So okay, fine. If a coin of mass M is placed gently on the top surface of the block, the top surface. Okay, right. M is okay. Cool. So yeah, you need an extra 1/5 volume buoyant force, right? Yeah, cool. So we need to figure out the volume of this thing actually. But the 4/5 volume stuff that, right? So let's just say each, so 1/5 of the volume, right? The buoyant force of that is B. Then 4B is equal to the weight, right? So 4B is equal to the weight of our block. Then right, when you have like 5B or that extra B, which is just 1/4 of the weight of our bigger block, that is equal to the weight of the mass, right? Our new mass, okay, so like coin. So small m times t, right? And of course the weight is just capital M times t, right? So mass m, right? We don't care about edges or whatever, just capital M. Yeah, so just small m equal to capital M upon 4, of course. Wait, something's not right about this. Yeah, one extra point 4, so it should be that. Huh? Am I missing something? No, how could this be? It has to be weight upon 4. Oh, okay, you want capital M, not small m. So, okay, that's going to be 4 times of small m. So just see the answer. Next question. 19th. A boy carries a fish in one hand and a bucket not full of water on the other hand. If he places the fish in the bucket, the weight now carried by him is still the same. What? Yeah, it's still the same. Depends upon his, no, same as before, right? Why would it depend on the speed though? Yeah, I have no idea. Okay, 20. We just think about the vertical force, right? That's our weight or something. Okay, a cork of density something floats on a calm swimming pool if the fraction of cork's volume, which is okay, the of fraction of cork's volume, which is under the water, is okay, right? So 0.5 can answer. It's just half of it, of course, because yeah. So half of it's yeah, half of it, of course. 50%. Leave the answer. Anyone? Two cylinders of same cross section and length L. You know what? I think we should stop here because I'm not sure whether or not we have more time. Okay, so we'll just stop here. Let's see you in the next video.